So hi everyone, it's Alex, and today I'm gonna walk you through some memory editing and game hacking. I'm gonna show you some relative basics. It's a bit beyond basics, but it's still not gonna be hard. I'm gonna walk you through my methods that I developed over the years and how I think about stuff while I'm working on some title or problem, and how I try to solve the problems. So what we want to do, for example, is get infinite health in some game. Today's game of choice is Ice Age 3, Dawn of the Dinosaurs. It's a kids platformer, but it's actually not a bad platformer in my opinion. And also, this game is a good example of something very interesting that you'll see later, because most of the games require you to do either less or more to be able to hack them. This game is kind of a perfect middle example. It's not really like hard, nor it's actually that easy. So first thing we're going to do is try to hack our health. And the second thing that we're going to do is create a complete God mode. Now the God mode is basically when you are completely untouchable by other objects. I mean, by other enemies at least. So anyway, let's go. So the first thing that I like to do is analyze the executable. I like to fire up DE. DE is detected easy. It's a little handy tool that can show you like certain internals of the file, the PE, portable executable, because this is an exe PE file. You can also see the same results. Here, the header starts with MZ. That's the initials for valid PE file. PE file are Windows executable files. The standard is called PE32. So we just found out that this is 32-bit exe, and that's all that we really needed. So let's start the game. Now this game doesn't support windowed mode, but at least it's not exclusive full screen mode. I'm gonna use my controller to play the game. Let's just start a new game. Alright, over here on the left top corner of the screen is our health. First we need to find some enemy.
Get him, Sid.
Alright.
We'll be right behind you.
Now as you can see, one enemy just hit us. It's okay to think like that every piece of health is worth maybe 1, or it could be worth 10, or it could be worth any number that the developer chose. But let's think logically and say, okay, no one is crazy to set like HP to number 7 for 1 bar. So let's say that this is worth like 1. So one circle on the screen is worth like 1 value. We're going to try to use the cheat engine to actually search for the values in the memory. Now, cheat engine is one of the few programs out there that can search through the RAM memory for any values that you want. It can do much more than that, as you'll see, but for now we're going to use that basic feature. So I'm going to try to skip a lot. So as we saw on the screen in the game, our health is now 4. So let's say that indeed inside the memory this is number 4. Now 4 can be stored as a byte. I'm going to show you this with the calculator. This is 1 bit. 8 bits is 1 byte. So this is 1 byte, this is second byte, this is third and fourth byte. 4 bytes is 32 bits. And that's called D-word, double word. In computer science, word is the term used for 16-bit or 2 bytes. A byte is, as you can see, 8 bits, 1 byte. There's keyword 64-bit and D-word 32-bit. So this doesn't matter right now, but in general, that should be known. The maximum number that we can set here is all ones, because as you can see, number 2 is 10 in binary. Because in binary, you can have only 0 or 1. So if you want a number 3, basically you're populating the spaces. You're going by power of 2. So this here is 1, 2, 4, 8, 16, 32, 64, 128. So if I type in 3, the first 2 numbers will be populated. First 2 spaces. See, number 3. Number 3 is 11, binary or 1, 1. Now number 4 will be 1, 0, 0, because this is 1, 2, 4. So to represent 4 in binary, you only need to check this bit over here, and you don't want any other bits. So number 4. So number 5 would be 1, 0, 1, right? And number 6 would be what? 1, 1, 0, and number 7 would be 1, 1, 1, right? 1, 1, 1, 1 is 15. Now, to represent the next number, 16, we need to use the other half of the byte. So number 16 is 1, 0, 0, 0, 0, as you can see. We're using the other upper half of the byte, because we do not have any more space in the lower half. And basically, if I set all the zeros to ones, the 255 is the biggest possible number we can represent. We added the 128, 64, 32, 16, 8, 4, 2, and 1. The point here is 255 in decimal is the maximum value that you can store in one unsigned byte. if you have a sign byte, which means it's not always positive, it could be also negative, your maximum value will range from minus 127 to 128. What is important is this hex value here. Now, hexadecimal is a numbering system which computers use like all the time. And basically, no computer uses decimal internally. It just doesn't make sense for computers because they use binary at the end of the day. So for them, hexadecimal is much more natural because hexadecimal could be represented by the power of 2, while decimal could not be. In decimal, you have numbers from 0 to 9, and that's exactly 10 different numbers. And then you create the 11th number using the previous 10 types of numbers. While in hexadecimal, you have more. I'm going to show you how the hexadecimal works now. 1 in decimal is 1 in hexadecimal. 1, 2, 3, 4, 5, up to 9. It's all the same. Then decimal doesn't have any more types of numbers. So basically, you need to create the next number using the previous numbers. While the hexadecimal have 6 more different types. And basically, they used letters from A to F. So after 9, if you add 1 now, it's going to be A. See, decimal 10 is A, plus 1 B, and all the way up to the F. F is 15. Now, hexadecimals also need to use the second digit because it doesn't have any more space here. So anyway, that's all that we need to know. And why did I talk about this in the first place? Because our theory is that the current health value is number 4. So our value can fit into 1 byte. So it would be logical to maybe start searching with the value type of byte. And that's what I wanted to show. These are different types of values that can be stored in memory. These are the complete basics of computers, like in general. What if the developers did not really care about memory optimization? They're like, why would I use 1 byte? We can use like 4 bytes because this is a 32-bit exe, this is 4 bytes, so we're going to use just integers. Now, integers and int represent 32-bit data types. So when you are using an integer, you're implying that you're going to use a number that could store a lot bigger numbers. Let's cut to the chase now. This is already taking too much time. So I'm going to use all. Why all? Because I'm not really sure what type the developer chose. All right, so we are down 1 more HP now. So let's look for number 3. We have some results, 209 results. So let's go back to the game. Let them hit us again. I accidentally let them hit me twice, so it should be number 1. We have some number 1s. If they hit me now, I'm gonna die. Sometimes in most modern games, when you die, the pointers in all the memory resets. So maybe we can just try one of these 4 values. Maybe it's still the right value, but we need to be more careful while searching. So let's start this again. Go to new scan, first scan, number 5, 4 bytes. Let's see. Now go back, it's still number 3. So here we have only 1 result. I'm going to try write number 5. So this is not the real value. So let's reset our scan, and instead of trying to guess what the developers used, we're going to use all and unknown initial value. This is what you use to just dump the memory without scanning, without searching for any specific values. This is game hacking. This is how one part, the most boring part in my opinion, looks. Let's scroll a bit through this. Oh, there is also this float, 30. Interesting. We're looking for values that make sense. Maybe this float, 30, is the real thing. Let's try 50 here. Oh, it seems that it is. Let them hit us so that we verify this is not the fake so-called screen value. Because some games have different values, like they use one true value for health internally, and then they use the different one, which is a copy of it, that's basically only for displaying the value on the screen. So right now we found our health, and it's float. That's interesting. I would never say the developer chose float. It's weird. This game uses floats as round numbers. Not really important. I'm just openly thinking right now. Anyway, we found our health, and we can now modify our health. We can check this box here, and the cheat engine will freeze our value. And when the enemy hits us, we are going to lose health, but cheat engine will revert it back really fast, like in less than a second. But there is a problem here. You need to have the cheat engine open all the time, and it's also possible to die this way, because if we encounter an enemy that in one hit can take 50 health from us, we're going to instantly die, because even though the cheat engine is really fast, it's going to return that health in less than a second, the game is still going to detect that before the cheat engine returns the 50 to the memory, the routines and functions for killing the player will immediately activate, so you're going to die. So we need something more permanent. Also, all of these values are dynamically allocated during the runtime of the process. So this address here will change after every restart of the game. For some games, it even changes after every cutscene, after every load, or, We now know what the value is, we can always search for it, but that's not the thing that we care for. We want to find a permanent solution to our problem and then later on work on something even more complex. We're going to find out what code in the source code of the game is responsible for actually changing this value. Like when enemy hits us, this goes down. There is a logic somewhere that says, oh, if player got hit, decrease the HP by 10, for example, per one hit, store that into the memory. This is why I explained hexadecimal numbers, because all the addresses are represented as hexadecimal numbers. There is a thing called breakpoints. It's a basic feature of every debugging job. There are software breakpoints and there are hardware breakpoints. Hardware are inside the CPU, the software breakpoints are different. There are special instructions. I'm not going to go into it right now. So we're going to set something called write breakpoint to this address. What this basically means, when the value inside this address changes, so basically when something writes the new value into this address, we're going to get notified. The cheat engine is going to show us what address was responsible for the change. As you can see, nothing is happening right now. We can go back to the game. If you go back, still nothing is happening. So when the enemy hits us, come on. All right. As you can see, the count is 2 because the enemy hit us 2 times. And there is an instruction here that's actually responsible for writing to this address. I'm going to try to briefly explain what's happening here. This here, inside the big brackets, this is the base plus the offset. So this base plus offset, in our case, equals this address over here. You can verify this. This is ADI here. All CPUs have these registers. They're like variables from math, if you remember, like X, Y, Z, whatever. Those are variables that the CPU exclusively use when manipulating data in memory. Now, those registers are the fastest possible memory that exists in a computer. So basically, CPU have a different, let's say, areas of memory, and registers are basically volatile memory. And they're insanely fast, but they are only temporary. They are very limited in space. So this ADI here, let's go to ADI. During the breakpoint hit, ADI was this value. So I'm going to add it here. And then if you add 348, we get 40AA0E8, 40AA0E8, as you can see. Anyway, it's going to store 30, our new health, into this memory location, this base plus offset, and this memory location is the location of our health in the memory. So what we need to do right now is click on the show disassembler. And now we are in disassembler. You see these bytes here, all of these bytes. This is how the program looks. Like the program is just a bunch of hexadecimal bytes that the CPU reads and interprets them as binary. So we humans have something called disassembler. It can take these bytes and specifically group them and then show them as much more readable instructions than just these bytes. For example, instead of reading 83EC08, we get sub ESP08. And instead of reading this D99F480300, we get FSTP DVERT PTR ADI plus 348. It's easier to read this representation than this representation. Anyway, this is our function. It starts over here. This is the beginning of the function. This is the end of the function. Functions always end with ret, which means return. So there is a function A that calls function B. When function B do its job, it returns back to the function A and continues. Basically, there are 3 instructions here. First is this load instruction. It takes our health, then it subtracts the damage from our current health and stores that result back into our health. Now, we have a few options. We can do anything here. We can modify this instruction to store something else in our health. We can do a lot of things. But the easiest thing, in my opinion, here would be there is this subtraction. We can just delete this subtraction. Now, you cannot ever delete any bytes. Like if you have a certain amount of bytes, like this application, for example, this exe is 7,216 kilobytes long. You cannot really delete any byte. If you delete even 1 byte or add even 1 byte, it's not going to work again. It's never going to run. So what we can do is replace this instruction with some different instruction. There is a handy instruction called NOP, which means no operation. We can add this code to the code list. This is our code list now. It's like a bookmark thing. And we can right click and there is replace with code that does nothing. We're going to replace this with 4 NOPs. NOP, because NOP instruction operation takes only 1 byte. So if you go back to the game now, we're going to let the spider attack us, and as you can see, we will not lose any more health. But I cannot kill the spider now. What does this mean? I intentionally did it this way because I wanted to show you the side effect of this. In this situation, in this case, in this game, this is the side effect. There are games that are programmed differently, and you can do this, and it's gonna work only for you. This tells us that the game is using a shared decrease health routine. So basically, the programmers wrote a decrease health function, and they call that decrease health function for you and for enemies. So it's the same function for you and for enemies. We can prove this. We can set a breakpoint to see all the addresses that are changed by this instruction, by this code. I'm going to hit the spider. And as you can see, there are two instructions. One is our health, and this is spider. This means that we just discovered and proved that this function, this instruction, and this called function is actually shared between enemies and player. And this is why at the beginning of the video I said that this is nice middle example difficulty game. What we can do it in this situation. We can write a script that's going to somehow distinguish between us and enemy. The first thing that I would look at is some patterns. So we are looking for some obvious pattern. Like, is there like anything that's kind of, I don't see really anything. ADX is 0 here, I see that. I'm not really sure. What would I do in this case? We can also set a read breakpoint in this address and see, is there any code that reads, doesn't change, but reads our health, that doesn't read the health of our enemies. You can do this by right-clicking and find out what axis this actually. I'm going to increase the health of our enemy so we will be able to hit it. And I'm going to freeze both my and my enemy's health so I can do some tests without the enemy dying or me dying. So I'm going to set a read breakpoint on my health, and I'm going to set a read breakpoint on my enemy's health. I'm going to hit the enemy, then let the enemy hit me. The enemy is accessed from 5 different places in the memory, and we are accessed from 8 different places in the memory. So F18D, we do not have this F18D address here. C59E, C59E is not here. So we can use this. Let's, for example, go to this code. What I like to do is I like to find out what address this instruction accesses to be sure that it only accesses the player. I go back to the game, see it only reads the player. And basically, I think it reads like once every frame. It reads the health once every frame, which is very good. This is almost perfect. We are going to inject our script, our code, our change here. Actually, we need to inject the 2 places. This is the first place. Because this code only accesses our health, we are sure that this thing is unique for us. And we can use this to make a script. In this situation, base is ACX. Now, if you remember from the last time, here our base is ADI. So the idea is to write a script that's going to save this ACX value, grab the ACX value from this instruction, from this place in the memory here in this function, and is going to save it into a variable. We are going to create our variable. Then in this function, we're going to create another injection point and redirect the code to our script. And the code here is going to compare ADI with the value we gathered from the ACX over here. And if they match, that means that this is player. And basically, we are going to disable this instruction. Otherwise, for every other entity in the game, we're going to just let it slide. We can allocate memory in the process. We can ask the operating system like, hey, can you give us some memory to write our code into? And then we will redirect this code to our memory. And after it finishes, it's going to continue from the next instruction. We're going to use code injection. We are going to allocate 1 kilobyte of memory. We're going to allocate a bit more memory. We're going to allocate like 64 bytes. And we're also going to register the symbol. We can use something called DD, which means define double word, and set 0, which means reserve 4 bytes and set their value to 0. We're going to copy the ACX, which is the base, into our pbase. Syntax of the Intel x86 assembler is instruction or opcode destination source. So copy from ACX to pbase. Oh yeah, we also need the enable and disable section. When we save this as a script, when we check the box, this enable part will happen. When we uncheck the box, this disable part will happen. That's just how the cheat engine works. Let me show you how does this look now. When I enable this instruction replaced by jump to our new allocated code. This is our instruction that we wrote, move ACX into the T base, then it's going to do the original instruction because we still need the original instruction to happen, and then it's going to jump back and continue where it left off. Now we're going to inject here at this fsub point. We're going to create another code injection. Let me just rename this new mem to fetch, just to be clear what it is. This will be called help. We're going to compare CMP instruction to compare the value of T-base with ADI. We're going to write a comment for future references, for example. So the idea is that if this is a player, we're going to skip this instruction, and if it's not player, we're going to do this. There are probably more elegant solutions, but we don't care about them right now. So this is the simplest thing that we can write. We're going to jump, if not equal, to the original code. And the original code is going to be defined here. But if it doesn't jump, which means if it is player, if it is equal, then we're going to skip this instruction and just do this instruction and return to where it left off. Let's now incorporate this into our first script. So this is our final function. Let's try our code. Let's show you what's going to happen. So this is our second batch. Instead of this original code, our second jump will happen. It's going to compare ADI with T-base. As you can see, ADI right now is 0. If it's not equal, it's going back to original code. If this is enemy, it's going back to original code. But if it is player, then it's going to just store the health without subtracting it. So basically, it's going to take the same health and just store it back. Then it's going to jump back to where it left off without ever subtracting the health. This is just one way of doing it. So everything should work now. We'll let the enemy hit us. As you can see, the health is not decreasing, but we can kill the enemy. So that would be it. As you can see, we successfully managed to do this. I didn't show you like more than half of what I planned initially, but this took too much time already. Next time, I'm going to show you how to make the God mode that we talked about. So yeah, that's it. See you in the next part some other time.